Hello everyone. I am Dr. Gagan Khanduri. Uh, I have done my PhD from Electronics Department of IIT Delhi. My PhD topic was semiconductors. I have done my MTech from Physics Department of IIT Delhi, and I have been a member of IEEE since last 12 years. I am a member of Indian Association of Physics Teachers and member of Indian Physics Association. I have been I worked as senior scientist at IIT Delhi. Um, I have more than 9 years experience of working in the industry. Uh, I have been ex-director and associate professor of physics in different engineering colleges. I am net qualified in physics and I have also qualified the GATE exam. I have been teaching JEE, NEET and physics for 11th and 12th class students since 2014. So let's talk about a topic that is very dear to my heart and which is about semiconductors. Uh, so, uh, what is a semiconductor? So, as you can see on the screen, that this semiconductor is called as silicon, and this one is germanium. Okay. So, why exactly are we studying semiconductors, and why do we use it, and where do we use it? So this is the question. Okay. Okay, so this is the famous silicon and this is the germanium. Both of these are semiconductors, and in the early stage uh, the engineers and scientists used to work with germanium, but later on they realized that silicon is a better candidate to be used as a semiconductor. So the question was, uh, exactly do we use semiconductors? Okay, so consider a situation that you are a businessman and you have a company in India and you work with a company in China. Okay, so there is a language difference. You are very well versed in English and Hindi, and the person in China, he knows only Chinese. So, to get the most benefit out of this present situation and to develop and grow your business, it is necessary that there has to be someone who can interpret what you both are um, exchanging, how you are exchanging your views. It must be interpreted by someone, right? So semiconductor is something like that. It can speak two languages, not literally, but yeah, in the sense, in the electrical domain, semiconductor can speak the language of insulator, and semiconductors can speak the language of a conductor. So the question arises is, what is a conductor and what is an insulator? So, when we talk about solids, we can differentiate them, categorize them uh, on the basis of their conducting properties, right? So, when we talk about conducting properties, we mean how easily can they provide a path to current. So, it eventually comes down to how easy it it is to flow the charges, right? That is current. So, conductors can do it very easily. Okay. Okay, so conductors can flow current easily, Insulators, they won't allow current to flow through them, right? So no flow of current. So semiconductors are in the midway, right? They may choose any of the sides. A semiconductor may allow a current to flow through it easily, or it may totally stop the flow of current. So how it does that? Of course, you have to help it, right? So we do that by doping it. Doping means we add some impurities in it. Okay. So doping means adding impurities. And impurities most common are boron, phosphorus, and there are some other like aluminum, antimony. Okay, so why semiconductors would start behaving uh, like a conductor or an insulator, depending on the doping that we do. Uh, to understand that, we have to understand what is the basic fundamental difference between the conductor, semiconductor, and insulators, and that we can only understand when we uh, look at their band structure, that how they are being formed. Okay, so let's check the conductivity of some uh, common materials about which we have heard. So the electrical conductivity, that is the easiness to let the current flow through them at room temperature. So temperature is important. It's quite different for each of these three kind of solids, that is conductors, semiconductors, and insulators. Okay, so suppose if I am talking about silver, right, its conductivity is in the order of 10 to power 7 ohm per ohm per meter, right? Copper, it is almost competing with the silver. They are the best conductors that we can have. And as you go down the list, there are alloys like constantine and nichrome, which are used in like meter bridge and other applications. So here the conductivity has dropped from 10 to power 7 to it has dropped to 10 to power 6 and 10 to power 5 per ohm per meter. Okay. Now you look at the carbon, germanium, and silicon, which are semiconductors. For carbon, it is 10 to power 4. Germanium, it has come down to 2.2. So it is a 10 to power 7 order of difference between a germanium and silver. For silicon, it is far less, 10 to power minus 3. So the difference between a silicon and a metal like silver is of the order of 10 to power 10. Okay. So there is a big difference. So silicon is not going to let you flow current through it at room temperature. Okay. So if you look at insulators, the conductivity has reduced to 10 to power minus 11, minus 15, and up to minus 18. So for conductor, it was for about 10 to power 7 per ohm per meter, and for cards, which is an insulator, it has come down to 10 to power minus 18. So there is 10 to power 25 orders of difference, right? 25 order of difference. So this is a big difference. So the this universe has material which can differ in the property of allowing the current to flow, which is called conductivity, and the order of difference is 10 to power 25. So we, as a human being, we are going to make use of this property, right? And this is what we do. So how it comes about, from where this property is coming? Okay, so we have to understand this. So to understand this, we have to look at band theory of solids. So it is a quantum mechanical theory, and to understand semiconductors, we have to understand this. Okay, okay. So we this is a theory of bands, and bands of what? The bands of energy, where free electrons can be present. Okay, and then this theory also talks about forbidden energy gaps between these energy bands. So these are forbidden energy gaps. It means no free electron can be there, and in these energy bands which are allowed, electrons may be present, right? So these two basic structural property of bands will decide if an element will become a conductor or insulator or a semiconductor. Okay, so let's go through it. Suppose there is just one atom. Okay, so say a hydrogen atom is there. So we know what is its configuration. So there would be a proton in the nucleus and a electron. We may say for modeling purpose that an electron is revolving around it. Okay, so it can be represented by a mathematical function, which in quantum mechanical terms is called a wave function. So there would be a positive charge, that is a proton in this case, and the electron is moving around it. So we can represent it as a mathematical wave function. Okay, so it looks something like this in mathematical terms. Okay, so suppose there are two hydrogen atoms. What happens then is two separate hydrogen atoms. So we know what is happening there. This nucleus, this is electron revolving in this orbit, and there is then another hydrogen atom which has a proton and it has its own electron. So they are not overlapping. So the electrons are far away and they do not interact with each other. So we call these two separate atoms, and their wave functions are not overlapping. So this wave is up to here and this wave is up to here. But what happens when a molecule is formed? So let's see. Okay, so you can see here then when something like this happens, suppose this proton and this orbit of electron, so this atom and this atom come very close. So what will happen? Okay, so what actually happens is this orbit and this orbit, which is nothing but an energy level in which electron is allowed to stay and revolve, this same orbit cannot hold both the electrons because of the Pauli's exclusion principle, right? Because there is no way that you can differentiate between these two electrons, because all the four quantum numbers are going to be same. So because electron is a matter particle, it cannot have all four quantum numbers identical with another electron. So effectively, to uphold this principle, this single energy level of this electron and this single energy level of this electron, they merge together and they form two separate energy levels, one with a slightly lower energy and one with a slightly higher energy. So actually initially there is one energy level for this electron, one energy level for this electron, and when they are coming together, it this violates the Pauli exclusion principle. So there has to be another energy level so that the fourth quantum number can differentiate. Okay, so this is called the splitting of energy levels. So effectively, one energy level is going to be split into two. Okay, what are the consequences? Suppose in place of molecule you are going to make a solid. Okay, so in a crystal, the atoms are coming close together, right, to make a solid. So electrons are interacting with each other, and there are so many neighboring atomic cores. So many atoms are there. So suppose six atoms come together and their energy level starts to interact. So what is going to happen is, in place of six levels, six individual separate levels, we are going to have 12 levels. So effectively, six atoms coming together with same energy level are going to show 12 separate energy levels. And what will happen if in place of six atoms 60 were there? So you will find 60 energy levels on the set, right? They have to come take in all the 60 levels here, something like this. And the same thing is happening here also. They have to make 10 more levels between these six, right, so that it can become 60. So what you are going to see here, these are not separate levels now, they have become bands. Okay, so this is the band theory of solid, right, bands of energy. So this is going to happen when a solid is formed. Now the question arises is, what makes it a conductor or insulator or a semiconductor? Okay, so let's check it out. Suppose I have silicon here, right? So silicon has 14 electrons, atomic number is 14. So they are going to be adjusted in 1s2, 2s2, 2p6. So 6 to 8 to 10. So remaining are 3s2 and 3p2, right? So these are the four valence electrons. For a single silicon, this is the way it is going to arrange its electron. But what about when silicon is going to make a solid? So look, what happens is, suppose this is the these are the core states, that is 1s2, 2s2, 2p6, right? And this is your 3s2 and 3p6 state, right? So this is your p state and this is your s state. We know that there are two seats for electron, right? In one s state there can be two electrons, okay, and in a p state there can be six electrons. Okay, now suppose there are n atoms which has come together, n silicon atoms have come together to make the solid silicon. So what will happen is, in place of one s state we are going to find two n states, right? Because every one s state is going to have two states for electrons. So n atoms will have two n states for the s orbital. Okay, what about p state? Each p state can have six electrons. That is, they have six states for electrons to come and sit. But if there are n atoms, the states will be six n states. And as I have said here, that in s state there would be two electron, and in p state also there would be two electrons. So in if there are n states, there would be 2 into n electrons already present there, and there are 2 n states, so this is filled, 3s2 is filled, right? So it will also happen to these 2 n states of s. But what about p state? There were 6 seats for electrons in one p state, but there were only 2 electrons present, so 4 seats were empty. Now that there are n atoms have come together, there will be 4 n seats will be empty. Okay, so let's call it region A. Region A is when the atoms are almost isolated. Okay, so as soon as they start coming together, these S state and P state will merge and they will split in 6 n states in P, where 2 n electrons are present, and 2 n states in S, where 2 n electrons are present. So S states are filled and P states are empty up to a certain level. Okay, now when they come more close together, what happens is these states, this single state is going to split. So 6 n states split like this, right? Split like this, and this S state will split into 2 n states. So this is the splitting of that single P state into 6 n P states, or n states, which has 6 n seats for electron. Okay, and there are 2 into n electrons in these states, which can sit here, and these are bands actually, right? So this is S band and this is P band. Okay, we call it region B. So splitting of level is happening in the region B. Now in region C, you can see that the lower end of this P state has come down and upper end of S state has gone up. So they have merged. So this whole thing from here to here, this is one single band, and this is where the metals form. Okay, so region C is where the metal would form or a conductor would form. Okay, now suppose you bring atoms more closer, right? Or the stable configuration of silicon is not it at this distance. Okay, and you are bringing the silicon atoms closer, further closer. So what will happen is these states which was merged together, they will split again. So one band is going here and the other band goes like this. Okay, and this, then you can see that this, there is an energy gap this much, where in the lower end you find 4 n states and 4 n electrons. So all the states, 4 n states, are filled with electrons, and after this energy gap where no electron can stay, you can see that on the upper side there are 4 n states, but they are all empty, because the total electrons were 2n and 2n, that is 4n. All the 4n electrons have come here, right? And the states here are 4n. So this is totally filled. All the sites, all the seats have been taken by electrons. Okay, what is then there is an energy gap, and then there also are seats, but there are no electrons. So there are 4n seats, but no electron is present here. So this is where semiconductors and insulators are formed. So this is region D. Okay, so I will clear it in the next slide. I know it has, I have shown you quite a bit of things, but okay, anyways, so these are all the things, but eventually the lower states which were filled by electrons. So let's check out a semiconductor. So the what I was saying, that these all states, there are 4 n states and 4 n electrons. Here there are 4 n states but 0 electrons. So this is semiconductor, and this is the same thing is happening to say, insulator also. So if this is insulator, these are all filled states, and these are totally empty state, but there is no electron. Okay, so both the things are same, but there is a big difference, and the difference is of the energy gap. So here the energy gap is small in semiconductor, but in insulator this gap is big. And it so happens that whatever you may do, whatever the temperature you may rise for this material, no electron can jump from this valence band to this conduction band. But in the case of semiconductor, if you raise the temperature, electron will start jumping from valence band and going up to the conduction band. So why does it matter to me, and how it makes a semiconductor different from conductor? We will see it. But in any case, we can look here that we have some definitions that there is a valence band and there is a conduction band. So when I showed you that figure and I said that okay, something like this is happening, there is a energy gap. I represent it as Eg, and there, so the upper band is called conduction band, and the lower band, right, this is called valence band. In the case of semiconductor, we have seen that this is totally filled with electron. There is no space for electron to move. All the seats are filled, and in the conduction band there are no electron. The seats are there, but there are no electrons to fill them. Okay, so this is the basic idea about conduction band and valence band. And in case of metals or conductor, they are somewhat merged, or the valence band is not completely filled. Okay, so I will show you in the next slide the idea. uh, but one thing is certain. I here you can see that when I was explaining insulator and semiconductors, the structure is not different. The only thing different is the width of this energy gap. So inherently semiconductors are insulators. So there is no basic demarcation between insulators and semiconductors, and this is very important because in the exam of NEET 2020 there was a question which confused many students, right? So I will try to clear that doubt. Okay, but the fact is that there is no clear demarcation between insulators and semiconductors. For simplicity or for categorization, we say that okay, if the band gap is of up to 2 electron volt, we will consider it as a semiconductor. And if the band gap, the energy gap is more than 2 electron volt or more than 3 electron volt or more than 5 electron volt, we will consider it as an insulator. Okay, so that's an important point. Okay, so let me help you visualize it. Okay, so in conductors, something like this is happening. The conduction band, the upper band, and the valence band, right, the lower band, they are merged, as I had shown you in the figure, the region C. And for semiconductor and for insulators, the conduction band and valence band are not merged. They are away from each other. A distinction is there that for semiconductor, the energy gap is smaller, say about 2 electron volt, and for insulators the energy gap is large, say about 9 electron volt. So 1.1 is the range for silicon, and about 9 electron volt is the range for silicon dioxide, which is a insulator. So if I may help you in visualizing this, let's look at this. Okay, so the conductors may form in two ways. One thing is that the valence band, which is this one in this case, because the last electrons are here, it is not totally full. So there are seats in which electrons can jump and move, right? So electrons can move around here in this free space. Here electrons cannot move because there is no space to move. So it is something like this. If you visualize it, I have tried to explain it. So look here. So this band may be represented by this road, right? Think about this car. It cannot move unless the car in front of it moves. So situation is something like this for this band. Electrons cannot move freely, and in this case, actually what is happening is there are cars everywhere. So no car can move effectively. What about this? This thing where there are electrons and there are free space to move is like this part of the road where there are less number of cars and most of the road is empty, so the cars can move with larger speed, faster. Okay, so a faster electron would give rise to a higher current. Okay, so this is a conductor. Okay, there a conductor may be formed, which is the merging of valence and conduction band. So you may think of it as a suppose this was the lower end of conduction band and this was the upper end of conduction band. This is the top end of valence band and this is the lower end of valence band. So these two roads have effectively merged. So any car can move in any way wherever it may find the free space, right? So they can actually move very fast, right? So this is if they are moving faster, it means that electrons may move fast. So it is a conductor. So what happens to semiconductor and insulators? Let's check. This band, this is the valence band. This is like this road. It is completely filled. I had told you that it has 4 n states and there are 4 n electrons. So you can look it here. All the space is taken by cars. No car can move back or forth, right? They cannot move. But if somehow someone removes this gap, this partition, these cars can move from here and they can move actually faster. There will be space for these cars also then, and the cars which have moved to another lane, they can also move faster. But who is going to remove these barriers? And temperature may remove them, right? The energy may be given by the temperature. So these cars can move up to this empty road. So this is what happens in semiconductors. Uh, what about insulators? So for insulator also there is a empty space and there are lots of car and no empty space here, just like this scene. So this is this, and there is a completely free road just above it, right? Like this. But no car can move from here to here. The jump or the problem that it has to face from going here to here is too large. That means no temperature can raise an electron from here to here. Why? Because the gap is too large. So this is what is happening to insulators. They have lots of cars, lots of electron in valence band, but no empty space to move around. Semiconductor, they also are like insulators, but they have an advantage that if there is a large enough temperature, they may remove this barrier, they may force this barrier away and jump around from this lane to this, and then they can move freely. Okay, it is a hard concept, but okay. So there, most of the time in semiconductor, from semiconductor topic, one thing that comes as a question in board exams and also in the NEET exam and JEE exam is the resistivity versus temperature, right? So for conductors, the curve is shown like this. Okay, so for a typical conductor, the curve will start from here somewhere, right? There is a some resistivity, initial resistivity at 0 K, 0 Kelvin, And as you raise the temperature, in the start it goes something like this. It's a curve, and then it becomes a straight line. This is a curve between resistivity and temperature, and you are raising the temperature from here to here. So resistivity is increasing. At low temperature, this thing, right, I have highlighted it here. You can see it that it's a curve. Okay. So the question arises is why temperature, an increase in temperature gives rise to an increase in resistivity of conductors. Okay, that's the reason is, suppose this is a metal, right? So it has lot of free electrons which can move around. So it can flow a large amount of current. But you have to keep in mind that their positive ions are still here, right? And when electron come into uh, the region of effect of this positive ion, it will reflect, right? It will get attracted, and then because of its initial velocity, it will change its path. We call that a collision. So there are collisions, right? And every time a collision happens and the electron will leave its path, right? The question is why electron is moving like this, because there is some positive end of a battery and there is negative end of a battery. So electrons are moving away from the negative end, and because the unlike charges attract, it is moving towards the positive end of the battery. But suppose there is a plus ion here and the electron will get collided with this positive ion and then change its path, so it will take time to reach the positive end of the battery. Okay, so effectively these positive ions are going to make the electron transverse this path traverse this path after taking a longer time. Every collision will make the electron to change its path, and so effectively the drift velocity will reduce and the current will get reduced. Okay, and if the current is reduced, I would say that resistance is increased. Okay, now suppose you are going to heat it up. If you heat this metal or this conductor, what will happen is these ions, they will start vibrating, right? Anything which gets energy, it will start moving and vibrating. These are vibrating because they cannot get free, right? They are there due to some metallic bond, right? So these bonds, they will stretch like this, right? And the atom which was standing, ion which was standing like this, now it is vibrating. What will happen is the path for electron which were moving along quite nicely earlier at low temperature, now at higher temperature they are going to collide more with these ions. So effectively the relaxation time will get reduced, right? And the drift velocity will decrease. So the current will decrease. And when we say that current has decreased, we say that the time for the charges to pass through has increased. And this time phenomena is quantified by the term of resistance or resistivity. So as the temperature increases, resistivity increases. For what? For whom? Metals or conductors. Okay. What happens to semiconductors? Let's check it out. For semiconductor and insulators, suppose this is a semiconductor. Okay, but when I'm showing you a semiconductor, I have to take into account that there is a conduction band which is empty, and then is a valence band which is filled. Okay, so it does not have any electron in the free empty space. All the electrons are crammed up here. They cannot move. Suppose I raise the temperature, what will happen is some of the electrons will get high enough energy to jump this energy barrier and come into this empty space. and as soon as there are these electrons come into empty space, they can move freely. So actually temperature has given it free electrons where there were none earlier. So conductivity is going to increase, right? Of course, you may say that what is happening to the vibration of those ions? Won't they increase the resistivity? Of course, it will increase the resistivity. But earlier, there was no current. But now there is current, and these electrons which has jumped here, they will leave behind the holes, seats, and now these electron also can move from these seats to this seat to this seat, and eventually to the positive terminal of the battery. So we call them holes. So effectively temperature has given rise to free electrons and holes. Okay, so where there was no current flowing earlier, there is some current. So effectively, as you raise the temperature, the resistivity has gone down because some current has started flowing. Okay, so and for insulator also this is going to happen, because there is on the only difference between semiconductor and insulator is band gap, right? For high enough temperature, some electrons may go up to the conduction band of insulator also. Okay, so I have got a reference where we can see if for insulator this happens or not. So these are the curve for some of the insulators that are used in industry and in science research. So you can see that this AB, this AB is a carbon resistor. Okay, it is called Allen Bradley resistor, and for it you can see that as you raise the temperature, the resistivity has gone down. Okay, for sphere also, this is also a resistor. It moves like this. For CG, this curve, this is also a resistor. Okay, this G100 and G1000, these are the germanium resistors, and yes, the curve goes like this for them also. Platinum, a metal, you can see that as temperature rises, resistivity is increasing, right? There is no surprise there. But for resistors, it is coming down, and for insulator also, it is coming down. The reference is of G. White. The book's name is Experimental Techniques in Low Temperature Physics, a book published by Oxford University Press in 1979. Okay, so this year's NEET exam, there was a question. The solids which has the negative temperature coefficient of resistors are. So most of the students have ticked this, because as the temperature increases, the resistance goes down, and most of the books talk about the semiconductors only, but the correct answer would have been insulators and semiconductors. Okay, one other question was there in the 2020 NEET exam. Which of the following graph represent the variation of resistivity with temperature for copper? So copper is a metal, so this cannot be correct, this cannot be correct. So you have to choose between this one and this one. Now this portion is very important. If they had shown it like this and then this like this, it would have been the correct option, right? But they have shown just the curved path part, and we know that for copper this should be the correct answer, right? So for copper, this brown one, you can see that it started something like this and then it became linear, right? So it was a tricky question. It cannot start from here itself, it has to show some curve path and then it becomes linear. If they had made just this change, this would have been the correct answer. But anyway, it has become a quite long video, so I would stop it here now, and thank you for watching.